So the last time we went over how to set up a system of equations in order to solve for the linear regression through a bunch of points, and we tried it for a couple of examples. And sort of what I glossed over was this point of, well, why this line rather than any other line, okay? So what do I mean is the following. So here's, once again, one of the 3-point data sets that we had. So the 3 points are in blue, and the red dashed line is a solution of the linear regression solved for by the / command, like the way we constructed it. And you're looking at it, it's like, oh, that's a fair way of going through those 3 points, but it really doesn't seem like the only way of going through the 3 points. Why is the slope exactly what it is? I mean, why is it like this instead of a little bit more shallow or a little bit more steep? Why are those solutions not the ones that popped out? Okay, so the question here is, why do we have this particular line? Okay, and the answer to that question is that it minimizes. This is a particular line that minimizes the error. Defined in the following way. Okay, so here's our plane where we have our data, have our x and y. And we had our data points, which were something like the following. And here was the line that best went through it, okay? What I mean by error is that I'm going to take my data points, and I'm going to call the line, the linear regression line, my prediction. So here's my best guess. My best guess is on this dotted line. So the error is defined as the distance between every data point and my best guess of what that data point should have been in a noise-free world, and I'm going to take that distance and square it. Okay, so I end up with those squares over there where the sides are determined by the distance between the line and each of my data points. And next I'm going to take the area of each of these squares and add them together. And that's what I mean by error. I am telling you that the line that we fit by the method we just talked about is a line for which this error is the smallest. Okay? To be a little more explicit, I'm going to define the error as the function evaluated at every x point. So in this case, this will be our linear line. So specify 2 parameters, the slope and the intercept, minus whatever the data had been collected at that particular point. I'm going to take that distance, I'm going to square it to get the area of every one of those squares. And I'm going to add it together for all the data points, all n of my data points, okay? And then I'm going to divide by n. And some people prefer taking the square root of this entire thing, but that does not change the fact that however you define it, if you define it this way, or if you define it by the square root of this quantity, it remains the case that the linear regression solution minimizes the error. Okay, because the smallest error by this weight is also the smallest error if you take the square root of it. Okay, so I'm going to show you how to compute the error in the model fit that we just computed. So going back over here, remember this is what we had before. We had the 3 data points, and we constructed the V matrix, or solved for P, and we plotted both the data points as well as the linear regression. Okay. So to compute the error, I'm going to follow this formula that we have here, and I'm going to type it in so that we can evaluate big E as the error. So here we go. What we're going to do is we're going to make a vector of errors, and I'm going to call it errors, and I'm going to say that it equals y. Well, let's do it the other way around, like the way I actually wrote it on the board. So it's going to be slope, oh, not right there, slope times x, so these are my x coordinates, plus intercept. So this is my model prediction, right? This is my linear regression prediction of what's going to happen. And I'm going to subtract the actual data point y from it. Okay? And next, I'm going to square this whole thing, right? I'm going to take the square of the whole thing, element by element. And then last, I'm going to take the sum of that quantity. So let's do that in a separate line here so it's a little more obvious what I'm doing. Okay, so here is the errors, point by point, right? So this should be the same size as x and the same size as y. And what we're going to do now is compute big E, which is the sum of all the errors. So that's this sum term here. We're summing over all the points from 1 to n, and in this case being 3. And then we're going to divide by 3, which is the number of elements in x, which corresponds to the number of data points that we have. So if we compute that, we will see that it equals 0.0952. Okay, so that's great. So now let's do something fun. All right, let's say you don't believe me. You don't believe me that this thing is actually the thing that minimizes the error, and you think you can do better by guessing. All right, let's try it. Let's try guessing different slopes and intercepts and see if we can possibly get a value for E that is smaller than this number here. Okay, so how do we do this? Well, you can do it by hand, or you can just guess. Okay, so let's say I give you 100 guesses. All right, so n guesses equals 100, and for every guess, I am going to generate a value for a slope. So a guess slope, and let's say this is going to be a number. So what was the range of the numbers we were looking at? Okay, I think both of those values are positive. So P had been, so the real answer was 0.21, and the intercept was close to 1. So let's say that my guess is going to be a random number, one single random number, and I want it to be between -1 and 1. Okay, so this will give me a random number between 0 and 1. I'm going to multiply it by 2, which gives me a random number between 0 and 2. Subtract 1, which gives me a random number between -1 and 1. And now I'm going to make a guess for the intercept, and I'm also going to generate this by a random number. And let's say that, oh dear, here we go. I'm going to generate this as a random number between -2 and 2, because that's what I'm going to guess. Okay? So what I'm going to do now is, using this guess model for the line, I'm going to evaluate a value for E, and we're going to compare it to the actual E that we got from linear regression. So let's see. What's going to happen is guess E equals the sum of G slope, guess of the slope, times X, plus guess for the intercept, minus Y. Oh, that's not Y, that's 7. Minus Y. I'm going to take the element by element square of all of that and sum up the entire vector. And once again, I'm going to divide by 3, which is the number of elements in X. Okay? And I am going to then keep track of all of these values for the guesses. I'm going to initialize it as an empty vector of zeros with n guesses in it and 1. Okay, so just the 0 vector. And every time I make a guess and compute the linear regression, I'm going to keep track of that number as the ith element of GE. Okay, let's see how that works, and we're going to run that. Okay, so now we have our value for E, which is the error from the linear regression, and I've just had 100 random guesses of lines that could possibly be better than the line that we got from the linear regression, and we evaluated the error from every single one of them, and now we're going to compare what they are. So we can visualize this by just looking at all of the GEs. Okay, so we're going to plot GE as little red dots, let's say, little red dots. I'm going to take a hold on, and we are going to plot a line, a reference line, that is at the value of the actual E. Here we go. Wow, that's interesting. Okay, so what's happening here is that it's been plotted, but interestingly, all of the numbers are down here. They're really small, but except there's one gigantic number that's right here. So that's throwing off the scale of our plot. So I'm going to just rescale the plot so that we can actually see the differences. Okay? Oh. What actually happened is that my code was wrong. Instead of I going from 1 to 100, all I did is I equals n guesses, which means that it only computed the 100th number. So let's fix my bug, and that's what happened, right? So the clue that that was happening, let me show you again how I did this, was that after I looked at it, right, I saw that all of the values for the red dots were actually at exactly 0, which is really suspicious. And I'm thinking, why are they exactly 0? Well, because they were initialized as 0. Why did they remain the value they were initialized at? So then I went back to my code and looked at what I wrote, and I saw here, which is that I wasn't actually going through all the values of 1 to 100 for I. Okay, so that's how I debugged that particular one. And besides my obsessive need to hit Control S at all opportunities, let's run this code, and that looks a lot better. Okay, so here's the result that we're actually looking at. So I had 100 random guesses, and so on the horizontal axis we have each of those 100 guesses. There is a red dot for the error evaluated by this formula of each of those guesses. So every time I pick a random number for a slope and I pick another random number for an intercept, I use that as my line, and I plot the error here, the red dot. And on the bottom, it's so low right down here that you can barely see it, is the blue line that represents the error from the linear regression. And it really is way smaller than all of the other errors. Now, if you don't believe me further, I'm going to plot this a different way. And what I'm going to do is plot another figure where we are going to plot, instead of both the error and the guessing errors, we're going to plot the guessing error minus the true error. Okay? And we're going to plot these as red dots as well. So if you see it this way, you'll see that every single one of these numbers is greater than 0, which means that the error from the guessing is always larger than the error from the linear regression. And so this is by no means a proof. It's simply a demonstration of something that, that you should remember, which is that linear regression always minimizes squared error, as drawn by this diagram. And this holds true even if you have a gazillion points, and we'll generalize on this topic in the next lecture.